All right, redox in a nutshell. So what is redox? Redox are reactions involving the exchange of electrons between two elements. So usually a redox reaction, or what happens is that you're going to give one atom to lose electrons and get the other atom to gain electrons. So how do you identify when this is happening? Let's take a look at a reaction and see if we could identify what redox looks like. So I put charges here. I don't need you to focus on how to figure those out yet. We'll go over that in the next slide. What I want you to focus on is what's happening. You see how this is going from a charge of 0 to a charge of positive 2. Whenever something becomes more positive, we call it oxidation. Same respects here, you see how you're going from positive 1 to a 0. You see how it's become more negative. Whenever that happens, we call that a reduction reaction. Now, redox reactions have to occur together, meaning you need to have oxidation and reduction occurring simultaneously in order to have this reaction occur. So if something is losing electrons, something else has to be gaining them. That's just the way it works. So I want you to fixate on right now is that if you become more positive, you're called oxidized or undergoing oxidation. If you become more negative, you're considered to have been reduced or undergoing reduction. So let's take a look to see how we identify these charges to get a better idea how to determine when redox is occurring. So first what we do is go over how to assign oxidation states. Oxidation state is a fancy way of saying charge. So rule number 1, atoms of an element, not an ion, has an oxidation state of 0. So anything in its elemental form, like sodium in its normal form as a solid, charge is 0. Magnesium, 0. Lithium, 0. Mercury, which is a liquid at room temperature, that's normal form for mercury, charge is 0. Diatomics, all diatomics are 0. So in case you forgot your diatomics, the way you remember it is with Hofbrinkel. So it's your mnemonic to remember these. So these are all the diatomics. Each combination representing the elements. So this is H2, O2, F2, Br2, I2, N2, and Cl2. So if you have F2, oxidation 0. Br2, oxidation state 0. N2, 0. So any diatomic oxidation state is 0. Oxidation state of an ion is the same as the charge. So what if you have an ion? So if you have an ion, whatever the charge is, that is the oxidation state, because that's what oxidation state is. So for this one, it's positive 1. For this one, it's negative 1. Moving on, oxygen is negative 2. So O is always negative 2 except in this molecule. So this is the only time it's not negative 2. And when you see it here, it's actually a negative 1 charge. So whenever you see oxygen and hydrogen peroxide, H2O2, it's going to be a negative 1. Otherwise, it's a negative 2. Fluorine is always a negative 1. So whenever you see F, just consider it negative 1 and move on. Hydrogen is always a positive 1 in covalent compounds. So in case you forgot covalent compounds, they're compounds involving two nonmetals, 2 or more nonmetals. So for example, HF is a covalent compound. So in this situation, F is a negative 1, H is a positive 1 according to these rules. H2O, covalent compound. What's the charge on H? Positive 1. Why? It's covalent compound. That's what it O is in covalent compounds. Ionic compound's a little different. We're not going to get into it, but basically, if you have an ionic compound, like let's say KH, that's actually going to have H as a negative 1 charge. This is an ionic compound because you have a metal and a non-metal. But in the covalent compounds, O is a positive 1. 6, the number of oxidation states should equal to the charge of the compound. So if there is no charge, you assume it's 0. So how do you know there's no charge? Well, look at some examples. All these, except for the last one, don't have a charge in the upper right-hand corner. So these all would be 0 overall. This one down here would be a negative 3. So let's go over these and figure out how to do oxidation states. So the first one we're going to look at is O. So you have a negative 2 for O. So on the bottom, what I'm going to do is put the individual charge of the ion or the element. And then what I'm going to do on top is put the overall charge coming from that element. So what do I mean by that? Well, I'm going to multiply this negative 2 times the 7 to get the overall charge. How much charge is the O's bringing in overall? It's negative 14. Do the same thing with K. It's positive 1 individually, 2 of them, so positive 2. Chromium, I skipped over to potassium, and the reason I did that is because I know group 1A, 2A, and 3A have set charges, right? And those set charges are basically positive 1 for group 1A, group 2A is always a positive 2, and group 3A is always a positive 3. So because those charges never fluctuate, I can use that to figure out the charge on them when I see them in a compound. Chromium is a transition metal. It's got multiple charges. You don't know which one it is, so leave it for last. So as a general rule, leave transition metals for last. So what's the charge have to be from chromium? Well, it's negative 14, positive 2. This has to be a positive 12. Why? Positive 14, negative 14 gives me 0. That's what I'm shooting for because there's no charge on the compound. What's the charge on each chromium? 12 divided by 2, which is a positive 6. This is the oxidation states I'm interested in. The top is for accounting purposes to help me understand what the charges are. But what I'm interested in is the bottom numbers. All right, go to this one, negative 2, 4 of them. It's a negative 8. Manganese, I'm going to skip, transition metal. Potassium, positive 1, positive 1. So what does manganese have to be? Well, 0 overall, right? So positive 7 gives me 8 overall, and negative 8, that's 0. What's the charge of each manganese? Well, there's no subscripts, you're just dividing 7 by 1, so it'll be positive 7. So there's my oxidation states. Moving on to this one, negative 2, 3 of them, negative 6. So what does iron have to be? Positive 6. 0 overall, right? Individually, 6 divided by 2, 3. So once again, to go from the bottom charge to the top, multiply the charge by the subscript. To go the other way, from the top to the bottom, divide by the subscript. That's how we got these numbers. All right, over here, we have FeO. O is negative 2 again. Was Fe to be positive 2? That was easy. So there's my oxidation states. Here, no charge, 0. Remember, if you don't see a charge on a right-hand corner, it's an individual element, it is 0. All right, here we do have a charge, negative 3. So I'm going to start with my O's as usual. That's negative 8. So what does P have to be? Now, ordinarily you do positive 8 and negative 8 gives you 0, but that's not what you could do here. You need to get to negative 3. So positive 5 and negative 8 gives me negative 3. That's my charge. 5 divided by 1, positive 5. There's my oxidation state. So that's how you figure it out for different elements inside of a compound. So how do you remember if it's oxidation or reduction? Well, there's some mnemonics you can use to help figure this out. First off, loss of electrons is oxidation, Leo. So like Leo the lion. So anytime you lose electrons, it's oxidation. How do you know you're losing electrons? It's on the product side. So anytime you see electrons on a product side, that's a loss of electrons, and it is always going to be oxidation. Now you could have also figured this out by noting that, oh, I'm going from 0, positive 2, I'm becoming more positive, that's oxidation. That's fine too. What do you look to see if there are electrons on a product side or reactant side to determine what's going on? Or do you look at the charges? Either way it works. So reduction, gain of electrons is reduction, GR. So look at this reaction. You say you have electrons on the left side. So you're gaining electrons. Gaining means it's on the reactant side. Once again, you can go positive 2, 0. Oh, I'm becoming more negative, that's reduction. Or you could say, oh, electrons on the left side, that's reduction. Either way it works. Put these two together, Leo says GR, because lines say GR. So this will be an easy way to remember that losing electrons is always oxidation, gaining electrons is always reduction. Or you can just fixate on where the electrons are located. It's really up to you. Either way works pretty well. So basically, if you see electrons on the reactant side, it's reduction. If you see it on the product side, it's oxidation. And that's as simple as it gets. All right, so let's look at this from a reaction standpoint. We have a piece of zinc here. We have copper sulfate inside the solution. What we're going to do is put the zinc in there. You notice how it gets darker? And if you look over to the right, you see how it's going from darker, now it has a brownish color. Where'd that brown come from? So obviously a chemical reaction occurred, right? But what is that chemical reaction? Let's look at this submicroscopically. So this is what happened. You have all these copper ions in solution hanging out, and then you have the zinc metal. Turns out that zinc and copper undergo a redox reaction. So zinc will give its electrons to the copper, and by doing so, it makes copper ion turn to solid copper. You can see that here. You see you have a solid copper now where their zinc was. And that's because the zinc, the solid zinc, lost its 2 electrons and went into the solution. So you're losing 1 zinc ion and you're gaining 1 copper ion on top of this. That's what the reaction looks like. And it's an exchange of electrons. So let's look at this from a reaction standpoint. This is what happened. The zinc lost 2 electrons. See, it's on the product side, it's being oxidized. And those electrons were given to the copper. The copper took those 2 electrons and became solid copper, and that's what you see. So there's your oxidation reaction, there's a reduction reaction. Remember, you need to have both to have a chemical reaction that's considered redox. And if you let this go long enough, more of the copper ions will take the place of the zinc, and more zinc will become zinc ions. So what's the end result? Your mass of zinc metal will decrease because you're losing it into the solution, and the copper ions from the solution will eventually find its way on top of this metal. All right, let's see if we can identify oxidation reduction. So the first reaction, you see how you're going, and you're going from a 0 to a positive 4. You could look at that and say, oh, that's oxidation. Or you could look at it and say, oh, there's electrons on the product side. That's always an indication of oxidation. Either way works. Next one, same thing. You're going from positive 3, positive 2. Notice that you're becoming more negative. That's reduction. Or you could look at it in terms of, well, I have electrons on the reactant side. Anytime I have electrons on the reactant side, that is also an indication of reduction. Finally, the third one, you're going from a 0 to a negative 1. You could look at it and say, oh, become more negative, that's reduction, easy. Or you could look at it in terms of electrons are on the reactant side. Either way works. All right, what if you have a complete chemical reaction and I ask you to figure out what the oxidation and reduction reactions are? How do you do that? Pretty easy. So here you see you're going from positive 2 to a 0. So it's a positive 2, this is 0. Anytime you're going from a more positive to a more negative value, that's reduction. There's my reduction reaction. And here, I'm going from a 0 to a positive 2. What is that? That's your oxidation reaction. So what you're going to do is build what's called a half-cell reaction. What is a half-cell reaction? We're going to separate the oxidation reduction reaction into two different reactions, just so we could understand and see it better. So I'm going to start with the oxidation reaction. So you have Mn being turned into Mn2+. Now you notice the charge on the right side is positive 2 and the left side 0. They have to be equal to make this a proper reaction. The other way you can look at it is that in order to have oxidation, you need to have electrons on the product side. You don't see any right now. So how do I fix both issues? Simple. Put 2 electrons. Put as many electrons in the charge. Charge is 0 here. Charge is 0 here. There's my reaction. There's my half reaction showing oxidation only. Reduction, same logic. We're going to use the same exact approach. We're going to take Cu2+, draw an arrow, Cu. So where do I put my electrons? Remember, it's reduction. 0, positive 2. I'm going to put my electrons on this side. By doing so, overcharge is 0, overcharge 0, and also I have the electrons on the left side, which is what I need to show reduction. So either way works, and that's how you would demonstrate it. So why are we doing all this? We're doing all this to better understand batteries, not just redox reactions. So this is an example of a battery. First thing I want to point out is your electrodes. Your electrodes are the metals in the battery. So every battery has 2 metals. Could be the same metal, could be different metals, really depends. So the metal over here is zinc, the metal over here is copper. We have an anode and cathode compartment. That's what every battery has. So you're trying to tap into the whole redox thing, how it produces electrons, and use those electrons to create electricity, because that's what electrons are. That's what electricity is, the movement of electrons. And by tapping into those electrons, we can light this bulb. So let's go over the different components you need to be aware of. First off, the anode is where the oxidation occurs. So where's the oxidation occurring? Well, I'm going to tell you that your anode is always going to be oxidation. So this is your oxidation reaction. So if you identify oxidation, you put it in the anode. If they identify the anode, you call that your oxidation reaction. So basically we know that zinc here is turning into zinc 2+ plus 2 electrons. That's what's going on chemically here. Don't worry about the sulfate, that's just an ion that's already in solution, because you want the charge in this compartment to be overall 0. That's why we have sulfate to balance out the positive 2. It could be any anion, that really doesn't matter. What I want to focus on is what's happening chemically here. So zinc is producing zinc 2+. Here, what's happening is the cathode. So in the cathode compartment, we know it's your reduction reaction, right? So if it's reduction, we can assume that Cu2+ is taking up those 2 electrons produced from the zinc and becoming solid copper. That's what's going on chemically. So there's your oxidation reaction. We have zinc going to Zn2+ plus 2 electrons. So the zinc ions go in here, and because of that, the mass of this zinc electrode will get smaller over time. Those 2 electrons will go through this little wire connecting them, and go over here. Now, here we're tapping those electrons to light this bulb, but if there is no light bulb, these electrons will end up in the cathode compartment. The electrons would combine with the copper 2 plus, and then it'll produce solid copper, and this is what that looks like. And you can see that you're producing solid copper as a result of it. Now, the key to this whole thing is that you need two substances that will undergo this reaction. Not every combination of two metals will do this, and we'll go into which ones are which later. But the main things you understand is the anode is where you have oxidation always, cathode is always reduction, electrons always move from the anode to the cathode, so electrons always go this way. You need to have the charge in the compartment add up to 0. So as many cations you have, you need anions. And you also need a salt bridge. So what does the salt bridge do? As you add more and more zinc ions, this thing's becoming more and more positive. Remember, we want 0. We don't want to have a charge other than 0. You can't add any more sulfate in here. You already have as much as you're going to get. So how do you balance out this extra positive 2? That's what a salt bridge does. Salt bridge has a cation and an anion, and what it does, it adds it into these compartments to balance the charge. So for example, the salt bridge for this would be potassium nitrate, so K plus and NO3 minus. So as you're adding more and more zinc ions into the solution because you're producing those electrons, nitrate is going to start adding in here and balance out the charge. So for every zinc 2 plus you add in here, you're going to add 2 nitrates to make the charge stay 0. You can keep on doing that indefinitely until the battery dies. Same thing over here. You're taking solid copper and you're getting rid of it. So now this side becomes more and more negative. So every time a solid copper finds its way on top of here, you add 2 K pluses. And that's where the reaction occurs. So that's the nature of a battery. What you're basically trying to do is generate electricity by tapping into those movement of electrons. All right, the last thing we're going to go over is corrosion. Corrosion is basically a reaction where a piece of metal breaks apart into its ions. It's kind of like rusting. So here we have an example of rusting. So what I want you to do is look at the charges and see where the oxidation reduction occurs. So this is 0, right? Elemental state, 0, diatomic. Here you have a -2. So remember 2 times 3, -6. So what does this have to be? A +6. So individually this becomes a +3, 6 divided by 2. So you see how you're going from a 0 to a +3? What do we call that? Oxidation. And you see here, you're going from 0 to -2. What do we call that? Reduction. So that's what is going on. It's an oxidation reduction reaction. That's what rusting is. So what happens chemically is that oxygen from the air combines with the iron and produces iron oxide. And that's what rust is. This brown stuff you usually see for rust, that's iron 3 oxide. That's the nature of it. Now, for those wondering why is there water here, metals can't travel between themselves. They need some sort of medium to travel through. That's the point of water. So the electrons are able to travel through the water from the iron to the oxygen, and that's where the reaction occurs. So if you've ever seen rusting, it always requires you to leave something and have it get wet somehow. If it doesn't get wet, there is no oxidation reduction. Whether it's getting wet because of the morning dew, because it rained, whatever, you need to have that to have rusting. So that's what corrosion is. So you need iron, oxygen, and water. The electron travels from the iron, which is oxidized, to the oxygen, which is reduced by traveling through the water. And that's corrosion. So that's a very common example of redox in nature, when something breaks apart. You can corrode metals when you react acid with a metal as well. And there's other variations of it. But that, in a nutshell, is what redox reactions are.